Hello everyone, this is Chris here with another edition of Logic Without Math. I am going to introduce you to what is the exciting part of logic, which is the positive part. It's nice to learn about various fallacies and gain skill in seeing them in someone else's arguments. And let's face it, there is some fun in taking somebody else apart brick by brick. But the real value of logic is seeing what a valid chain of reasoning looks like, and using known patterns to make your own. If someone says, hey, if we buy a car with better mileage, it means more money left over at the end of every month. We could use that to go to more movies. And so more mileage means more movies. I'd immediately know this to be a valid reasoning because I walk around with this picture inside my head. And this is what you learn when being introduced to valid forms. Previously, I made a video that was the first of the series about categorical syllogisms. You do not need to understand that for what follows here, but it is available if you want to check it out. Now we will easily transition into the use of variables and truth functional connectives, or symbols, in what follows. The value will be that it will allow us to envision a picture of the structure of simple examples of valid reasoning and determine the validity of even very long and complicated arguments. It also allows us to determine the validity of any argument that has exactly the same form, regardless of content, and taking out the emotions by concentrating on form independently. From here, we will be dealing with both syllogistic and non-syllogistic thinking that exists within a broader propositional logic complex. As with syllogism, we will use letters as variables to indicate propositions. A proposition is a statement that can be meaningfully said to be true or false, even if we do not know which. In what follows, a simple statement will be a letter for that proposition alone, or with its negation. We can symbolize any proposition as P. Should we wish, however, to express its denial and say non-P instead, we will symbolize it with a tilde immediately preceding it. As with all symbols, we can define the tilde in terms of a truth table. The tilde means not P, or it is not the case that P, and that is all that it means. In ordinary language, to negate a proposition that everything is black, we could simply say that not everything is black and leave it at that. As shown in the truth table, a proposition and its negation will always have opposite truth values. Our denial of P will be true when P is false, and false when P is true. I can now quickly introduce you to a valid rule, which is the rule of double negation. When given a double negation, we can infer the positive and vice versa. In this case, we can say that the premise and the conclusion are equivalent, so it is actually a substitution instance, or rewrite, rather than an inference. In most cases, these rules will not be equivalencies, where we cannot also infer the premise from the conclusion. Now we go on to compound statements that connect simple propositions together. The conjunctive version of a syllogism is not syllogistic thinking, but rather a simplification rule that states that when given a conjunction of two or more variables, P and Q, we may infer any of the conjuncts separately. This is because a conjunction is true only when all conjuncts separately are true. If all of them are true, then any one of them must also be true. And so our truth table for the and or conjunction symbol, the ampersand. In textbooks, you may also see a dot used, or an upside down V known as a wedge. The associated valid inferences related to conjunction are the first rule of conjunction. Given P and Q, we can infer P and Q, and the rule of simplification. Given P and Q, we can infer P, or given P and Q, we can infer Q. A disjunction is a statement of P or Q. The symbol for disjunction is known as a vel. P or Q is thus symbolizes as P vel Q. In logic, we use the or in an inclusive sense when we use the vel symbol, meaning that we agree to P or Q whenever P is true or Q is true, without specifically meaning one or the other exclusively. If in the context of an argument we mean P or Q and not both, we can symbolize it in another way to make that clear. Our disjunction will always be true, except when all of its separate disjuncts are false. And so our truth table defining the symbol V or vel is thus here. And now the rule of disjunctive syllogism. When given a disjunction and the negation of either disjunct, we may deductively infer the other disjunct. So if given a statement P or Q, we know one of them has to be true. If P or Q and not P, then we can infer Q. If given P or Q and not Q, we can infer P, because if P or Q is true, one of them has to be. A hypothetical proposition is one that states that one proposition, called the antecedent, will imply another proposition called the consequent. I will introduce an arrow symbol to indicate that one proposition materially implies another, so that it's an if-then situation. So if the proposition if P then Q can be symbolized as P arrow Q. As statements in this context, P and Q are separately simple statements, while we call the P arrow Q, if P then Q, a compound statement that is itself a statement. It can have its own truth value that may be different from the truth values of simple statements and other compound statements that it may contain. A proposition of this type is only declared to be false when the antecedent P is true, but the consequent Q is false. This symbol as a truth functional connective can be defined by this truth table. Here, when P is true and Q is false, P implies Q, or if P then Q is then false and is true under every other condition. A statement of a bare variable letter with the tilde is still a simple statement, whereas the other truth functional operative symbols introduced here, the or, the and, the if then, connect simple statements into a compound one. An important thing to bear in mind here is to make sure you have the right meaning when reading or deciding in writing whether to have the tilde within or outside of brackets, because it can change what is being negated. As a general guide we have here that not P implies Q means the denial of P implies Q, and not bracket P implies Q is the denial that P implies Q. In words, the first statement might stand for, if Lassie is not a dog, then she is a fish. The second statement might be that it is not true that if Lassie is a dog, then she is a fish, or that Lassie being a dog does not imply that she is a fish. There are three types of syllogisms using what are called hypothetical statements or conditionals. The pure hypothetical syllogism simply takes a standard form in which it is valid only in that form. Otherwise, it is not very interesting. Given if P then Q and if Q then R, we can infer if P then R. The forms of modus ponens and modus tollens forms of hypothetical syllogism are more interesting in that they are far more commonly used, and each creates a sometimes amusing fallacy if used improperly. Under modus ponens, given a conditional and the affirmation of the antecedent, we may deductively infer the consequent. In the modus tollens form, given a conditional and the negation of the consequent, we may deductively infer the negation of the antecedent. However, these forms of arguments do not allow for the drawing of a conclusion from the affirmation of the consequent or the negation of the antecedent. An example of the fallacy of affirming the consequent is that if Bacon wrote Hamlet, then Bacon was a great writer. Bacon was a great writer, therefore Bacon wrote Hamlet. And an example of the fallacy of negating the antecedent is that if your dog is a cat, then he has a tail. Your dog is not a cat, therefore your dog does not have a tail. As with all formal fallacies in deductive logic, an invalid form can be shown to be invalid by the construction of the form that has true premises and a false conclusion. It is possible precisely because, in this form of argument, the truth of the premises does not establish the truth of the conclusion. Now I will go through some exercise questions where I state the kind of argument and check for proper form or fallacy. You can pause the video and come up with your own answer if you want. Number 1. Brown went to Boston or Barcelona. I know it was Boston because I checked with our people in Barcelona, and it turns out he didn't go there. Okay, we're starting off with a disjunction here. We have a Boston or Barcelona there that Brown went to. We have a statement. It had to have been Boston because it couldn't be Barcelona. It wasn't Barcelona. So it's actually a disjunctive syllogism of the form Boston or Barcelona, not Barcelona, therefore Boston. So this is a valid disjunction syllogism. Number 2. If you didn't steal a cookie out of the jar, you would not have chocolate on your face. You have chocolate on your face, so I know you stole a cookie. Now, in this case, we're actually starting off with a hypothetical proposition here. And it contains negations, but it's of the form, if not P, then not Q. And we'll go into more of that later. But for right now, you have chocolate on your face is denying that you don't have chocolate on your face. And therefore, I know it is also not true that you didn't steal a cookie or you stole a cookie. So this is actually a valid modus tollens form. Number 3. If she got good grades in school, then the teachers liked her. She was quite popular amongst her teachers, so of course she got good grades. Once again, we're starting off with a hypothetical proposition here. If good grades, then teachers liked her. The second premise is that she was quite popular and therefore she got good grades. So we look at this second premise here to see what is being affirmed, and what is being affirmed is in fact the consequent that teachers liked her. So this is the fallacy of affirming the consequent. Number 4. If we buy a car with better mileage, it means more money left over every month. We could use it to go to more movies, and so more mileage equals more movies. Okay, we're starting off with a hypothetical proposition, and it's if you think about the meaning of the rest, it's pretty apparent. We're talking about a series of hypothetical propositions here. So, if better mileage, then more money, and if more money, then more movies, and therefore, if more mileage, then more movies. This is the valid pure hypothetical syllogism that I introduced at the top of the video. Number 5. If my professors were any good, I'd have a better career, but obviously I had bad professors. Okay, once again, we're starting with a hypothetical statement. If my professors were any good, I would have a better career. In here, we have something unstated. We have a conclusion that is unstated and left to be drawn in the context as understood, that I had bad professors. That is a negation, and we look into the first premise, the hypothetical, and see that it is a negation of the antecedent. So that is the fallacy of negating the antecedent. There are three methods of proof that are popular and are explained in many textbooks. The method of formal proof that math geeks love involves setting up the premises and then drawing subsequent inferences, line by line, until the desired conclusion has been shown to be drawn from the lines above. And each line is a justification for drawing it from what came before, in many cases from the very rules I already introduced. It has value as rhetoric that explains itself as we go from here to there, and thus in a way it commands the respect that the other methods do not. But the weaknesses of it go beyond the fact that it is only learnable and usable among people familiar with truth tables, and thus knowing the meaning of what occurs in the justifications. There is also no formal proof of invalidity. It also requires imagination and practice, with a skill that gets reduced if not practiced. And just because I may not be able to construct a formal proof of some argument when commanded to do so, does not make a valid argument any less valid. The truth tree method that I prefer is actually a simpler way of finding an invalid row in a truth table without drawing it. But it assumes prior understanding of truth trees and a few of the logical equivalencies I'm going to teach here. Like truth tables, the trees can determine validity or invalidity. Trees overcome the difficulty of truth tables being time and effort consuming in complex arguments involving many variables. For instance, this tree involves 6 variables, and evaluating it by a truth table would require 64 rows. Truth trees are also another mechanical method that require little or no thought in carrying them out once learning the technique. Truth tables may be used to allow us to read off from the table the validity of an argument. Remember that for an argument to be valid, the truth of the premises must prove and thus be followed by the truth of the conclusion. We would expect that anywhere in the truth table that the combination of the premises are true, the conclusion would also be true, or we have an invalid argument. One of the least intuitively valid of the rules so far introduced has been the modus tollens. For example, let's show its validity in a truth table. The rule to be tested is P implies Q, not Q, therefore not P. In setting up columns, we will follow 3 steps. First will be the variables involved in the first set of columns, and we mark out the rows for the different truth value combinations possible. The number of rows will be 2 to the exponent of the number of variables. Next, we will put in any negations and compounds that will assist us in additional columns. We want to take care that we put our assigned truth values under the main symbol of the whole of a compound statement, for it is the symbol's meaning that is the proposition we are to evaluate. Next will be the premises and the conjunction of the premises, followed by the conclusion. Notice how in this 5th column I put the truth value assignments directly under the ampersand, the main symbol that is the truth functional connective of the whole statement at the top. What we are looking for in determining validity is a search for a counterexample of the asserted argument, where all the premises are true and the conclusion is false. That would prove invalidity of the argument being tested. The 4th row here is where we see validity showing itself. The 3rd and 4th column show the case where all the premises in columns 3 and 4 are both true, and a visual inspection of the conclusion in the last column shows it to be true as well. It is optional to also show the conjunction of the premises in the 5th column, which I find easier, but it also shows the conclusion to be true when the conjunction of all the premises are true. Whether or not you find it easier to have another column with the conjunction of all the premises or not, it is necessary to look at a situation where all the premises are true to determine validity or invalidity. Now let's try something not yet introduced. Not P and Q, therefore not P or not Q. In this case, there are 3 rows in which the premise is true, and in every case the conclusion is also true, meaning that it is valid. In this case, the one premise is at the top of column 6. There is another feature here that I want to highlight. You will notice that not only is the conclusion true when the premise is true, but also false when the premise is false. We say that they have the same truth value. Given that they have the same truth value, and given what we know about when a conditional statement is true, they must imply each other. That is to say, not P and Q implies not P or not Q, and not P or not Q implies not P and Q, as shown in this expanded truth table. These statements are equivalent propositions that, like double negations explained earlier, are substitution instances of each other. To express and define this situation, I will introduce the last special symbol that we need, the biconditional. We will use the biconditional symbol double arrow to symbolize the conditional where the antecedent and the consequent both imply each other. Where any P and Q materially imply each other, we symbolize their material equivalents as P double arrow Q, rather than writing the longer P implies Q and Q implies P. The rule of material equivalence states that any proposition P is materially equivalent to another proposition Q when they materially imply each other and they have the same truth value. And the truth table definition of the biconditional symbol is shown here. As we can see, when P and Q are both true, P double arrow Q is true. Or when P and Q are both false, P double arrow Q is true. And in the other 2 instances, it is false. As for the particular equivalence I just introduced, where the negation of P and Q ended up being the equivalent of not P or not Q, it is the discovery of Augustus de Morgan. His famous theorems regarding the equivalence of negations of conjunctions and disjunctions are: the negation of a conjunction is the disjunction of the negated conjuncts, and the negation of a disjunction is the conjunction of the negated disjuncts. To use truth tables to verify or falsify a proposed equivalence, we construct a table that will show us whether or not the propositions on both sides of the biconditional have the same truth value under all circumstances. Hence, we have this truth table here to prove P implies Q, double arrow, not P or Q. In this case, the validity of the biconditional is shown by the fact that it is always true in every row, because at the same time its constituents always end up having the same truth value. And so we now have the equivalence known as the rule of material implication. A conditional proposition is materially equivalent to the disjunction of the negation of the antecedent and its consequent. I have now introduced all of the equivalences you would need to know before learning about truth trees, and some you would need to know before studying the method of formal proof. There is another equivalence that I would like to introduce simply because of how commonly it is used in ordinary situations as well as in philosophy. Consider the argument: if you didn't steal a cookie out of the jar, you would not have chocolate on your face. You have chocolate on your face, so I know you stole a cookie. This, as I said before, is a valid use of modus tollens that is formally provable using the rule of double negation to translate the negatives into the positive conclusion. But it would also be surprising if nobody asks if we can't just transpose. If you didn't steal a cookie out of the jar, you would not have chocolate on your face into instead, if you had chocolate on your face, you stole a cookie from the jar. The answer is yes. Even in translating prose into symbolism, they can be written as C arrow S, as well as not S, arrow, not C. Thus, the rule of transposition. A conditional proposition is materially equivalent to the converse of its negated constituents. And finally, to show what invalidity looks like in truth tables, let's try to prove the fallacy of affirming the consequent to be actually valid reasoning. Namely, P implies Q, Q, therefore P. Here we see the invalidity showing up in the third row, where the conjunction of the premises is true, but the conclusion is false. And so it is invalid in its form. We have shown that there is a counterexample, that in one of the four possible truth value assignments for P and Q, where P is false and Q is true, the argument will have all true premises and a false conclusion. Row 4, where one of the premises is true but not both, is irrelevant. Regardless of what P and Q might be, one can always verbally spar to the effect of refutation by analogy, that it is like saying that if Bacon wrote Hamlet, he was a great writer, he was a great writer, and therefore Bacon wrote Hamlet. Now I will proceed to show how to translate an argument into symbols and construct a truth table having 3 variables. We will consider the following argument that can spark emotions, if not symbolized, to show its form. If people are entirely rational, then either all of a person's actions can be predicted in advance, or the universe is essentially deterministic. Not all of a person's actions can be predicted in advance. Thus, if the universe is not essentially deterministic, then people are not entirely rational. The first task is to assign variables to the separate propositions in positive form. So let's say that R equals people are entirely rational, P, all of a person's actions can be predicted, and D, for the universe is essentially deterministic. So symbolizing the argument, we now have R implies P or D, the second premise is not P, and the conclusion is not D implies not R. In constructing our truth table with 8 rows, the first variable has 4 T's followed by 4 F's, and the second variable alternates between 2 T's and 2 F's. Then the last variable alternates between T and F, giving all possible truth value combinations. In the conjunction of the premises, we will need multiple brackets, but it is the combination of them that we evaluate, whether in mind or on paper. Once again, this is an option just to make chart reading easier after it's done. In rows 3, 7, and 8, we see that the argument is valid. Each time you prove something, you discover a new valid form of argument, although as far as I know, this one has never been given a name. I won't bother trying to remember it either, but it is still valid that R implies P or D, not P, therefore not D implies not R. Well, that's all for now. I definitely recommend getting exercises on the web or out of textbooks you may find. I'll leave you with a summary chart, and I say feel free to take a screenshot. It gives you about 60% of what you would find in a textbook that explains formal proofs, where more is necessary. So if you like my videos, hit those like and subscribe buttons. Check out ways down below you can support my channel. Thanks for watching.